Hello everyone, welcome to the first lecture of the fifth module, which is on charge trap flash memory and 3D NAND flash memories. The disclaimers remain the same. Last modules we were looking at the floating gate cells, how they can be arranged to form NOR flash memories or NAND flash memories. Then we were also looking at their program and erase characteristics, the different physical mechanisms like Fowler-Northam tunneling, channel hot electron mechanism. We also looked at UV erase, and we were also discussing about the reliability concerns like SILC. We were also discussing about the endurance failure and all those mechanisms, then the defects and all, how they can be introduced in the tunneling oxide layer and all those things. So with that kind of understanding, let us go ahead and look at how these NAND flash memories are organized. So in NAND flash memory, what happens is the floating gate cells are connected in series to form what is known as a string. So these are your floating gate cells. So wherever you see the word lines, these are your floating gate cells. So these floating gate cells are kind of connected in series. And at the top, that is towards bit line, and at the bottom, that is towards your source line, we have two select transistors. And those select transistors are also in series. So now let us look at those select transistors. So we have this select transistor and this select transistors. This select transistor, the top select transistor is called bit select transistor, and the lower select transistor is called source select transistor. So what is the role of this? So in NAND flash memories, this bit line is kind of shared between different strings. So you have that string, you'll have another string like this. Source line is also kind of shared. So you'll have a source line connector of, so this is SL, let's say this is SSL1, this is DSL1. You'll have a BSL2, you have a SSL2, and these are kind of shared between the bit lines and the source lines. Now, if you want to uniquely kind of select one string, what you do is you just turn on these transistors. So, what is the use of these select transistors? So, if you want to uniquely select only one string out of several strings, you turn on this BSL and SSL. And then what happens? After you turn it on, suppose you want to read the characteristics of this cell, so you apply VPass to all other. VPass, that is a very high voltage, close to 5 volts, or that is close to 5 volts or 8 volts for 3D NAND flash. So you apply VPass to all others which are in series, just to kind of reduce any impact of their source resistance, like series resistance. And then the current that you read between this bit line and source line. So let me write that as well. So the current that you read, and that is the current which is flowing through the string. So what you read is a string current. And that string current is what? That string current is kind of proportional to the threshold voltage state of whatever cell you have chosen for reading. This NAND string kind of forms the basic element of this NAND array. And how they are organized is, there are several banks of these bit lines. So there is this even bit line and there is this odd bit line. And several such NAND strings are connected to these bit lines, to these bit line banks, I would say. So you have this bit line connected to several strings, you have that bit line connected to several strings, and then they also share common source line. So that is how these strings are organized within your flash array. Now there are several terminologies which are inherent to flash, such as page. So let me just write about page. So what exactly is a page? So page is a collection of all cells connected to a particular word line. So here you see that this word line 63 is kind of going through this string. It's also going through this string and will go through several such strings. Similarly here, if you look at this word line kind of goes through a cell in this string, a cell in this string, and it will also go through several such strings. So corresponding to this word line, all these cells which are kind of connected to this word line, they form a page. And what exactly is a page? What is its importance? So page is, the smallest addressable unit. So how can we address it? So it can be addressed using the row decoders. So the row decoder simply selects a particular page. That is, it simply selects either this word line or this word line or any of the word lines. It kind of activates that word line, gives all the other word lines to some pass voltage, and then when this word line is activated, you can kind of read these cells. But you want to read only one cell at a time. So then what you do is, then you kind of take help of your column decoder, which kind of selects the bits or bytes to be read. So if it is selecting the bytes, how it will select? It will kind of turn on either this DSL0 and SSL0, or it will turn on like something like DSL1 or SSL1. Actually here it's wrong. This should be DSL1. This should be SSL1 because your source is connected to that side. So yeah, it's wrong over here. Anyways, so the row decoder simply kind of selects a page, and then this column decoder selects the particular bit or byte to be like to be read or to be written, and that is how this addressability is done in this NAND flash array. Now another important part which you must have seen over here, another important term, is this block. So you have block 0, block 1. So what are these blocks? So your NAND flash memories are divided into several blocks. So what is a block? So block is nothing but it's the smallest erasable unit. So all the cells within a block are erased together. So you must have heard previously that your NAND is block erasability is kind of there in NAND. So this is what it means. So a block consists of different pages. So it consists of different pages, and you kind of organize it in blocks so that one block is kind of erased at one time. I mean, the entire block is erased at once. Okay. So now with this understanding of how the cells are organized in the form of strings, and how these strings are kind of organized and they are addressed in the form of pages or blocks, let us now go ahead and look at how these memory arrays, how these NAND flash arrays are organized in the chip at the chip level. So this kind of, like this figure on your left, kind of tells you how your memory block is organized in your chip. So if you look at the chip that is available as your SD card or as your USB stick or even in your SSDs, so you'll have something like this over there. So individual memory block will look something like this. So for sake of simplicity, let us assume that word lines are going in this horizontal direction, bit lines are going in this vertical direction. So what people do is, people kind of divide big NAND flash blocks, big NAND flash array into several subarrays, and these subarrays are known as planes. So usually, if you look at any of the modern NAND flash IC, be it 2D NAND flash IC or a 3D NAND flash IC, you will see that usually they will have 2 to 4 different planes on a single chip. And then the way they kind of organize the decoders and the peripheral circuit, that is really amazing. So if there are 2 planes, like here you have 2 planes. This is, let's say, plane 1. This is plane 0. So they always start naming by 0 and then you keep the name 1. So here you can see that the decoder is kind of placed between these 2. Similarly, if there were like 4 planes, so let's say if there are 4 planes, something like this on your chip, then they would place the row decoder. Let me use another ring. So then they would place the row decoder here and the column decoder here. So the way they pack this IC is really amazing. I mean, to achieve high densities, these peripheral circuit designers, these digital and analog circuit designers, they have come up with several, kind of not only pitch match, but also, they kind of fit everything within that small region between these 2 planes. So that is really amazing. So you know why decoder is used? Decoder is used to just first kind of, the row addresses kind of give you the address of a page, and then the column address will kind of select a particular bit or byte depending upon whatever addressability, level of addressability you have in the NAND flash array. And then one more thing I wanted to tell you, that here there's a difference between the sense amplifiers that are used for NAND flash array and the sense amplifiers that we use for SRAM or DRAM. So let me just talk about it. So you have these sense amplifiers. So you have these bit lines which will be connected to these sense amplifiers, right? Because at the end of the day, you want to read the memory state. And how you do that? You use a sense amplifier for that. So you have these sense amplifier. And what do you think? I mean, sense amplifiers are kind of redundant here. I mean, are they situated here, or are they kind of used here to make the process faster, or are they required for, are they necessity? So here also your sense amplifiers are necessity. Because what you read here is a string current. So you need to convert that string current into some bits, right? If it is a single level capability cell, then you need to convert it into either 0 or 1. If it is a multiple level capability, or a QLC or TLC, you need to convert it to several bits. So sense amplifiers here are also necessity. So okay, sense amplifiers are put like this. And what else can you comment about these sense amplifiers? Since they are reading currents, they have to be current-based sense amplifiers. Current-based sense amplifiers, which convert the string current to bits. Now, if someone is aware about sense amplifier design, then he would say that current-based sense amplifiers are actually difficult to manage, or their overhead is higher as compared to voltage-based sense amplifiers. So this is one of the directions where, whenever a new memory is discovered, sense amplifier designers have to kind of come up with a particular or a kind of optimized sense amplifier for this. And that is one of the major areas of research as well. Anyways, so with this, let me also talk about other peripheral circuitries or other elements of this block. So apart from these sense amplifiers, here you will also have some page buffers. So why these page buffers are there? So page buffers kind of store temporary data. You may remember this page buffer from our discussions on SRAM cell array design, right? So there also we had these page buffers where we kind of stored a byte or something like that. So here also we have page buffers which kind of store the temporary data. And then comes these peripheral circuits. This peripheral circuit over here. And these IO pads are just for connections to the outside world. I mean, the chip kind of, let me just write that first. So IO pads, your NAND IC communicates with the outside world only using these packs. Now let us talk about these peripheral circuitries that we have. So what do you think? These peripheral circuitries, should it be same as SRAM or it should be different? So it has to be different. Why? Because SRAM kind of works on the logic voltages. It works with voltages which is kind of close to the logic technology. That is, SRAM can work with VDD of 0.7 and all. However, since the physical mechanisms that you exploit in your NAND flash array is kind of CHE or FN, it's not CHE for NAND flash, but it's even FN is high voltage demanding. So the kind of voltages that you need to apply to program these devices. So we program or erase is in excess of at least 10 volts. So can your logic transistors handle 10 volts? No. Their oxide will burn out, or they won't be able to sustain these 10 volts. So what people use is, first, all the peripheral circuitry is made up of high voltage transistors that can kind of sustain these large values and even provide them very efficiently. However, once you go for these high voltage transistors, your area is very large. How much large? So these transistors can be in some micrometers. I mean, the gate length would be in some micrometers because they have to handle a large amount of voltage. Okay, so now with this kind of understanding, what are the different peripheral circuitries that you require? So first, you will need a charge pump, right? Because you need to apply such high voltages, and the kind of value of voltage that is available to you from the cell in your mobile phone or such IoT mobile devices is kind of 5 volts. So you want to convert that 5 volts to 10 volts or even higher. So 3D NAND flash, for instance, 3D NAND flash ICs require up to 20 volts for programming. So you can understand how much large voltages you are kind of playing with when you're using these NAND flash memories. So you need a charge pump that can convert your 5 volt battery of your mobile phone, the voltage that is given by your mobile phone battery, that is 5 volts, up to 20 volts. Then you need voltage regulators. I mean, they are kind of essential for all the circuits. Then you need level shifters. Why you need level shifter? Because you also want to apply VPass to some pages, right? So when you're reading one particular page, you have to pass this, like you have to apply this VPass, which is a high voltage, to the other kind of pages along that string. So these are kind of the peripheral circuits that are required for your NAND flash IC.